Welcome everyone to Evolving MBSE to Enable the Digital Future, presented by David Long. My name is Donna and I will be your host during today's webinar. For over 25 years, David has focused on helping organizations increase their systems engineering proficiency while simultaneously working to advance the state of the art. David is the founder and president of Vitec Corporation, where he developed Core, a leading systems engineering software environment. He co-authored the book, A Primer for Model-Based Systems Engineering, and is a frequent presenter at industry events around the world. A committed member of the systems community, David is a past president of the International Council on Systems Engineering, a 12,000-member professional organization focused on sharing, promoting, and advancing the best of systems engineering. Before David gets started, I have just a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. David will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be made available within 1 business day. The recording will be published to Vitec's webinar archive, located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Now I'm going to turn the presentation over to David. Welcome, and thank you for joining us.
Thanks, Donna, and thanks everyone for joining us today. If we're interested in systems engineering, we're all on this journey towards a model-based systems engineering. Depending upon where you choose to put the starting point, well, we're at a different phase of the journey, but some will trace it all the way back to the late 60s with the first computerized tools, the 80s and the 90s with the commercial tools. Many will trace it to the early 2000s, 2006 with the emergence of data standards such as AP233 and SysML 1.0. Regardless of where you trace it to, there's no doubt that every organization that knowingly is doing systems engineering is somewhere on a model-based journey. The question is, where are we ultimately heading? As Lewis Carroll famously said, if you don't know where you're going, any road will get you there. And as I've worked in the industry, as I've reflected personally over the last 18 months or so, I sense that we're beginning to get off track. Not that anything that we're doing is wrong, but if we ultimately want to get to the right destination, I think a slight course correction is required. Not a wholesale change, but a slight course correction in order to get to the digital future. So certainly there's a long heritage of modeling and simulation. We've been using models and simulation, well, they're fundamental to the way we conceptualize and execute systems engineering. What's critical in model-based systems engineering, or what we would characterize in this quote-unquote new age dating back to the 2000s, is a focus on, and really many, many options for the descriptive architecture. How are we representing our requirements, our behavior, our logical, our physical design? That's what SysML is about. That's what DODAF is about. That's what UAF is about in so many different ways. But if we come back, the fundamentals are still, well, it's still all about systems engineering. It's about connecting people, the required disciplines to address a transdisciplinary problem, eliciting their insights, bringing together their ideas. If you look at the CBOC definition, systems engineering is about ensuring the pieces work together to achieve the objectives of the whole. And when you talk about bringing things together, the fundamental risks exist at the interfaces. They exist at the interfaces of the subsystems. We know that as systems engineers, but they also exist in the silos, at the interfaces between the silos, between the disciplines. And so systems engineering doesn't act as really a controlling presence. It operates as a connecting presence. And so what is this journey to model-based all about? If you've been on this journey, you know it's about moving from ambiguity to clarity. So if systems engineers exist to serve as this technical connective tissue we are effectively translators. We are attempting to bring everybody together with a shared understanding and ultimately shared cognition of first the problem, the analytical concerns, the insights, etc., that bridge us from problem to solution. Whether you're using document-centric techniques or now model-based techniques, fundamentally, that's what we're trying to do. We're trying to work those interfaces in the subsystems and in the silos to effectively deliver a capability. So, before we talk about how we need to perhaps do a course correction of a few degrees on where systems engineering is going model-based, well, let's understand the evolution of model-based systems engineering. Just briefly, each of us is at a different point in this journey, but all steps that I'm about to highlight, well, somebody in industry is at that point. First off, let's really understand that it's not about seeing the big picture, it's about setting the big picture. As McChrystal described in Team of Teams, you cannot understand your part of the system, you cannot understand your contribution to the whole unless you have at least a rudimentary understanding of the whole. Some will call this system architecting, and that's fine. The key here is if we're on a journey towards shared understanding and shared cognition, we have to help the team understand the whole so that they can be effectively empowered to deliver their piece of it. Other than that, we cannot be agile, we cannot be aligned, we cannot be any of the things that we wish to be as we address today's problems, complicated and complex. So I will frequently deliver this simple message. In 2016, at the INCOSE International Symposium in Edinburgh, I heard an attendee say, it's 2016, can't we get beyond saying what model-based systems engineering is in all these presentations? And my answer is, well, unfortunately, no, because model-based systems engineering is now such a muddy term, the only way to address it is to actually declare what you mean. So for me, model-based systems engineering is all about taking both the descriptive and the analytical models required for systems engineering, making them more explicit, making them coherent, making them consistent. It's about an evolution in the way we represent knowledge, from relatively low fidelity representations in document to higher fidelity representations. In doing so, we've got better granularity, which gives us better information management over time. We do this for communication purposes and for analysis purposes. The engineer in us calls out the analysis, the systems engineer in us calls out the communication, and so on and so forth. The key here is really to lower the barrier of entry and to simplify the understanding, not change the understanding, simplify it, because this is evolutionary and we are seeking and should always seek to better represent knowledge. In doing so, though it's evolutionary, we can get transformative results. So in this evolution, what are we doing? Well, certainly if it's about shared understanding and shared cognition, we have to align and understand on the knowledge repository. Originally, we called it single source of truth. The language today is more authoritative source of truth. But if we each have a different picture of the whole, then we cannot deliver our part and believe that it's going to come together and come together successfully. Now, in the process, we do have to recognize that while we as systems engineers may choose one representation because it communicates effectively with us, by all means, if SysML works for you, there's a reason that Vitek and others support SysML. There are many other people who are involved in engineering systems: electrical, mechanical, software, reliability, business, customers, program managers, etc. They probably don't speak our representation set, but that's okay. If we have an authoritative source of truth and then blend the concept of fit for purpose, well, we can represent the same knowledge in many different ways. Again, the systems engineers are supposed to be the translators, helping to ensure that everybody has a consistent and aligned shared understanding. Okay, Once you've got your authoritative source of truth, once you've effectively aligned the team, well, now we can begin to use models to capture our reference architectures at a higher fidelity. So we don't go back to clean sheet of paper all the time. We can use higher fidelity representations to capture patterns, common problems that we see, and common approaches that we implement to solve those problems. In doing so, we can address the key or several key systems level characteristics: system health, system resilience, security, absolutely a system level characteristic. But again, because we are representing our knowledge in a higher fidelity way, we can now bring architectures, reference architectures to bear in a better way. Same is true with patterns. And we are beginning to go a step further. We're beginning to build up libraries of effectively components or subsystems, etc., so that we can begin to compose solutions at a model-based level. So rather than engineering down to the atomic level from a fresh sheet of paper perspective, we engineer to a certain degree, but then we can draw out of a library. Now, this can work at many different levels. It can be at the IoT level, Internet of Things. It can be at the system of systems level. It can be classic capability definition. But in each case, you're talking about using a concept of composability at the model-based level to enable the concept of composability at the systems engineering level. And then systems engineering is about, well, it's about system and it is about engineering. The system part of it is the architecture. It is setting the big picture. It is the one chance in the program you have the opportunity to get your hands around complexity. It's your one chance where you're going to define ultimately the system level characteristics: security, health, resilience, all those aspects. But then there's absolutely an analytical dimension that brings rigor. And so good model-based systems engineering actually connects those two. The architectural model, the descriptive model that moves us from first statement of need through logical, through physical and test, serves as the integrating presence for many different analytical models: a fluid flow model, a power model, a weight budget, etc. And we've seen these begin to be connected. They can be connected tool to tool, as we've done with things like our MATLAB connector and a Simulink connector that's forthcoming, as someone like Phoenix Integration has done with their model center, MBSE, which serves to, again, take that architectural model and use that as the coherent, consistent binding between any number of analytical models that are required to do MDAO and really effectively engineer at a system level. But now it's time to see the bigger picture. Now it's time for a little bit of a reality check, because we've been on this journey for about 10 years and we're starting to drift off course. Now, a big topic in systems engineering these days, and engineering overall, is actually how do we connect systems engineering and PLM, oftentimes framed specifically in how do we connect MBSE and PLM. So if we step back and look at effectively a PLM, product lifecycle management view of the entire engineering lifecycle, you'll see something like this. And if you did it in a complicated world, let's call it pre-model-based systems engineering, you effectively have all of these trees. You've got your requirement decomposition, your logical decomposition, you've got your design level bill of materials, et cetera, into the fielding. Well, this is complicated. This is old days, so we know things are going to move slow. We can do waterfall type approaches, and there's this air gap that we classically bridged with documents. Again, that was how we got shared understanding across the team. And as you left the conceptual design phase, you had requirements documents that were passed downward. Well, it turns out the engineering lifecycle is not radically different. We're trying to transform business needs, customer desires into a fielded system and support it through life. So we all know at our heart of hearts that technology always makes things better. After all, as Big Bang Theory taught us, Bluetooth makes everything better. Well, the reality is, if we take that existing process and simply apply digitalization to each step, it doesn't necessarily make things better. Again, going back to McChrystal, going back to Team of Teams, going back to the rising aircraft fatality rate in the 70s, where as we deployed more technologies, rather than things getting safer, we actually saw fatalities rise. Well, those technological advances that we tend to believe in on face value imbue the environment with nonlinearity, complexity, and unpredictability. And if we try to control complex systems using reductionist thinking, silo thinking, it's pointless at best or destructive at worst. We know this. We inherently know this as systems engineers because all of us could look at a car and realize, well, that's a system. And yes, I can break that down into its piece parts, and I can understand a motor, and I can understand a tire, and I can bring those together, and I can give great performance. None of us would ever instinctively think, hey, let me just grab the best engine I can find and the best tire I can find out of context, beyond fit for purpose, and bring them together and think that I'm going to get a performant car. We know that as systems engineers, but yet we engineer the system that develops systems different than we engineer the products itself. The phrase that I hear more and more in the community these days is integrating models. And the belief is I can simply take all my models, all my disjoint models that have evolved over time with different contexts and different purposes, and I'm going to integrate them. I'm going to take my independent silos and bring them together, and I'm going to get a strong chain. We know, if we will stop to think about it, that the design system is a system. And so the reality of model chains assembled this way is more held together with baling wire, duct tape, and bubble gum. It is not strong. It is not vibrant. It is not resilient. It will not deliver what we need to enable the digital future. We have to take the systems engineering that we know, the principles that we know for engineering our systems, and apply it to the way we're evolving systems engineering. Those who've heard me talk often hear me reference back to a lesson that I was taught by my father, the law of conservation of systems engineering, or if you prefer, the no free lunch principle. All this says, for those who haven't heard it before, is once you pick a problem, the amount of systems engineering required to successfully deliver a solution is fixed. For a more complex problem, it takes more systems engineering, less complex, less. Unprecedented, more, precedented, less. What you get to control is where you do that systems engineering. Do you do it early, up front, where it is highest leverage, or do you do it when most systems engineering is done at integration and test, okay, when things simply don't work together? Well, let's apply this to our own system. INCOSE knows that a system is a system is a system. After all, we're trying to look for systems practices in aerospace and defense and automotive and medical and energy. Well, we need to look at systems practices at the design system as well. The system, the engineering life cycle that transforms business needs into a productized system, whether that's product or enterprise or service, is a system in of itself. Here's the Lewis Carroll moment. The question is, if we look across that life cycle, should we be systems engineering? Should we be emphasizing model-based in our own world, or should we be engineering systems? Now, this may come off as a semantic game, a turn of phrase. and to a degree, maybe it is. But for those who've been around in COSI for a while, you may recall about 6 or 7 years ago, MIT was on a big kick, basically saying, you guys got it all wrong. It's not about systems engineering, it's about the engineering of systems. And to be honest with you, I thought MIT was being MIT and they just needed to be different than the rest of us. Over the last 18 months, I've gotten a little smarter, and I believe that MIT had it right. And it's all about perspective. When we talk about systems engineering, we are inward looking. We are in fact building our own silo for our own purposes and optimizing our own processes for our own needs. When we talk about engineering of systems, suddenly we are outward looking. We are looking across the entire engineering life cycle to better enable that transformation of business needs into realized capabilities. If we talk about systems engineering and model-based systems engineering, we're digitizing our own toolkit. If we're talking about engineering of systems, we're talking about how we better collaborate, how we better achieve shared understanding, how we better connect across the life cycle. Isn't that what we really need? In a static time, it's all about transforming requirements into capability. In a dynamic, changing time, it becomes ever more important because our team can only adapt and evolve to the degree we operate as a team. And so having systems engineering as a separate silo simply won't work. We can take that thought process and we can apply it to engineering the digital thread. In 2011, NDIA published this graphic as part of their roadmap for model-based engineering, what today we would call digital engineering. And part of the realization is it's only by connecting the life cycle that we get the business results that we're after. Lower cost, higher quality, shorter time to market. This is the perspective of engineering systems. This is the course correction that I believe that we must make. Other than that, we are optimizing ourselves for our own sake. So what does that mean? Well, let's apply systems engineering to ourselves. Let's apply systems engineering to this journey. The first thing is we have to solicit all the stakeholders, not just ourselves, but if model-based systems engineering is to be a connective tissue that better enables this digital engineering life cycle, it's more than the systems engineering team members. We tend to understand those very well. It has the corporate members, our champion, our management, the IT that's enabling, the process owners, but there are others with whom we must collaborate to truly understand the problem, see it from all perspectives, gather the necessary insights, and deliver a solution. It's the customers, so that we understand not the problem as framed, but the real problem. It's the users, so that we can deliver user-centric design. It's training, so that we can enable that. It is operations and maintenance, because it's a through life capability. It's other stakeholders that I haven't listed here. But step one, if we're going to engineer systems, is to see the broader stakeholder set. Step two is recognizing the information necessary to engineer a system. What we have done today, what we have done very well over the last 10 years, is transform the way that we bridge the air gap between systems engineers and detailed design, transforming from document-based artifacts to really a digitalization of the specification. And we've done so through a series of diagrams. That's important. It's necessary, but it's not sufficient. Product lifecycle management will often describe systems engineering as dealing with RFLP. Requirements, functional, logical, which is the logical physical design, and physical, the actual part instantiation of that design. But it's more than RFLP. It's the interrelationships, but it's more than specification. What's critical here is that we capture not only the outcome of systems engineering, but the journey of engineering as well, the journey of engineering that system. The why. Well, why do we care? Why is it important to capture the journey, the thought processes, the decisions, the alternatives, the rationale? Because it's actually the why that is critical when requirements change. When technologies are introduced and we want to consider, can we adapt it to a new technology? To engineering the next generation product, to evolving and engaging a distributed team, to even trust. If I'm only worried about the specification product, well, then I've changed the way I bridge that air gap, but I haven't really connected. If I want to truly connect this life cycle, it is not just specification, but it's also the why. Now, in doing so, we get to define the information needed to engineer a system. People can call that an information model, they can call that a meta model, they can call it any number of things. There is no agreed upon information model that underpins systems engineering. There is an information model that underpins systems engineering. If not, we couldn't engineer systems. But there's not an agreed upon standard. So what should you use? Well, you can use the S pattern from Bill Schindel at ICTT. You can use AP233. You can use Vitek's meta model that's been derived over the last 50 years of application. The only thing that I would ask you not to do is to invent your own, because this is not an easy thing to do. At least start with somebody's, but recognize if you're going to engineer the digital life cycle, it's not about representation, it's about information. Now, once you've got that, then you can begin to identify the real scope. We talk about connecting tools, and yes, we absolutely have to connect tools and models, but it's connecting tools and models in the context of information. It's about using information in the process of engineering. It's about gathering the right the right information and performing the right analyses to enable defensible decisions. The right decision at the right time, evidence-based. It's about supporting the people who need to come together, because people are where creativity lies and where insight lies. It's about the culture, because we're talking about knowledge management, and that's a cultural issue. Knowledge representation is a cultural issue. And then that scary T word at the very end there, trust. If you're an engineer, trust is a concept that you don't work on very well, certainly not at the people level. But if we're talking about the exchange of information, and we're talking about really some degree of transparency, trust becomes critical. If trust doesn't exist, I cannot reuse your model because I don't trust it. And by the way, I won't even give you my model because I'm afraid that you'll misuse it. This is the full scope of things that we have to consider. And so you begin to understand why using baling wire, bubble gum, and duct tape to connect together models really won't get us there. It'll take us off track. In doing so, we now need to look through life. It's not just the systems engineering phase. It's not just the design engineering of systems phase. It's through life. If I have a high fidelity representation at an information level, can I not use much better visualization techniques? Can I not begin to envision minority report type interactions? Can I not use the same core information model for conceptualization where I'm eliciting needs from the users and ultimately transforming that information model to a point where I can use the same thing to drive almost a gaming visualization in a training environment? We absolutely can engage and immerse through life. It's not just about a limited separate set of representations for us, systems engineers, and not a limited set of representations for the design stage. In doing so, we also have to recognize that those silos that exist right now in the engineering life cycle, they are largely being digitalized independently. We need to get above that. We don't need to be silo busters, okay? In some cases, the silos are perfectly fine. It's a matter of connecting them in the right way. In other cases, we're going to need to, well, maybe chip away at the silo a little bit, change some of the workflows, etc. Again, it's all coming back to what information do we need to successfully engineer a system? How do we tie those workflows together? How does the concept and theory upon which engineering is based operate on that information? There is a huge body of theory which systems engineering uses without ever being explicit. But if the information is explicit rather than implicit, then we can expose that information and make better use of this body of theory, game theory, decision theory, organizational theory, you name it. And in the process, we better underpin our workforce. That doesn't mean that everybody has to be an expert in game theory, but the information that we need and the interaction that we need to do our job is there in context. And, well, to be honest with you, it's defensible. Now, I've talked a lot about information because information is critical. We have to have the shared understanding moving towards shared cognition. But it's not a rote process to derive the right information, turn the crank, and get out the right solution. There's still the human side to this. And so as we look at how we transform our engineering processes and our engineering representation and even our visualizations, we have to keep the systems part in mind, the thinking. It goes back to fundamental principles. Processes, methods, and tools allow us to act informed by principles. But as we change the shape of the problems that we're dealing with, if I'm dealing with a human-centric problem, by the way, my methods and tools might be a little bit different. If I'm dealing with a learning system, if I'm dealing with a non-deterministic system, well, applying processes that have their roots in the 80s and 90s, that'll get me in trouble as well. So there is an information model that is consistent. It's operated on by processes, methods, and tools, but it's underpinned by principles. Let's not take the humans out of the engineering of systems. Humans are key. And while we're inviting the human into the engineering of systems, let's invite more than just engineers to the table. Because if we're going to re-engineer this engineering life cycle, as bright as we are, as experienced as we are, we need help from some outsiders. If you talk about the way information is represented, that is semantic science. That is a tough field in and of itself. Just because you or I might have access to the OWL ontology editor on the web, that doesn't make us an expert in the field. So we need to leverage that expertise, the same as we would leverage a mechanical engineer or an electrical engineer if we were doing those particular aspects. Visualization, I think if you showed Edward Tufte the visualizations that we are using for systems engineering today, well, he would probably have a stroke. So let's use some visualization experts to better represent, to better achieve shared understanding, shared cognition. This is all actually about people. Again, we're changing the way we're representing information, and in the process, we'll change workflows. Change. That's a people problem. Organizational change management is one of the biggest inhibitors to deploying model-based systems engineering and ultimately digital engineering. It goes on and on and on. The point here is any engineering exercise, any systems engineering exercise relies upon subject matter experts. We need to leverage these experts in making this journey a reality. So a couple comments on the journey forward. How do we get beyond, let's call it MBSE 1.0 to MBSE 2.0 if you'd like, or digital engineering 1.0, or whatever terminology you'd like to use. The terminology is not critical. It's recognizing the transformation that must occur. First, we just have to realize and drive home that change is necessary. Actually, maybe it's not necessary. Survival is not required. If we wish to survive and deliver capabilities as engineers or systems engineers, we have to recognize that traditional systems engineering, and by the way, traditional engineering, is no longer enough. The system scale is bigger than ever. The mission complexity, not just complicated, but complexity, is changing. Project teams are more distributed, more interconnected. There's complexity in that system as well through the supply chain, and dynamic complexity. The problems are changing shape as we try to solve them. We cannot apply classical, traditional systems engineering or engineering and expect that we can be successful. We certainly can't be successful within the time and budget constraints that we're being asked to solve problems and deliver capabilities. So the challenge is, will we apply our own practices to ourselves and the journey? Can we get a meta perspective on this problem? The reality is, people will connect models. They will connect tools. They will connect processes. Will they do so in an accidental way? Will they simply integrate them, glue them together, and hope for good things to happen? Or will we engineer them with deliberate thought so that we are doing integration of engineered capabilities as opposed to assembly of parts that we find? Systems engineering must live above the silos. Doesn't make us superior to the silos. We must live above the silos. That is the only way that we can see the overlaps. It is the only way we can define the seams, the interfaces. It's the only way we can see and address the gaps. It's the only way that we can preserve the why. And the why is ultimately essential. Not just the what, not just the how, but the why. In doing so, the meaning is in the meta model. The meaning is in the information model. If we're going to go to MBSE 2.0, if we're going to go to digital engineering, if we're going to get to the right destination, we need to stop talking about the drawings we want and start talking about the information we need. We must stop talking about model-based systems engineering as this disjoint thing, this new silo in the engineering life cycle. And we must get back to the MIT perspective, the engineering of systems. Ultimately, it's about enabling connected digital engineering in a complex world. This chart comes from, it's a variant of a chart from Eris in the product lifecycle management world. And the key here is we are after through life verification and validation, full traceability in multiple dimensions. I need to understand how my requirements are realized in a fielded system. I need to understand in a fielded system, particularly when things go wrong, how that traces back into the requirements and what changes I need to make to go right. But it's not that simple. It's multidimensional, because at that design phase, you've got all your models coming together, your architectural and your analytic. So it truly is a multidimensional traceability issue. If we're going to get to connected digital engineering in a complex world, we have to have that unbroken chain of traceability from requirement through serial number. It's beyond digital thread. It's richer. It's analytics. It's instantiation. You've got to have the information model that underpins this. We've got to have the richness of the why, because that's what allows us to evolve to changing conditions. Any weakness in this is simply non-negotiable and unacceptable, because we will fail to have shared understanding We will fail to have full life traceability. We will fail to have everything that we need to successfully deliver a capability. And so I've already said it, but I'll say it one more time. If we're going to make the journey to the digital future, it's not about optimizing model-based systems engineering for the sake of systems engineers. In fact, the path to optimizing systems engineering lies in sub-optimizing systems engineering. If you focus on optimizing systems engineering, you're creating a new silo, you're building walls around us, and we may excel, but then the whole system, the whole engineering life cycle begins to break down. That's not our job. Our job is to transform business level needs and requirements from first statement through a fielded capability. If that means that we have to sub-optimize systems engineering, so be it, because our job is to optimize the engineering life cycle. And then, well, if you want to be Russell Ackoff, you would say we fail more often because we solve the wrong problem than because we get the wrong solution to the right problem. I have the utmost confidence in our ability to engineer and find a solution to the problem once framed. The couple degree course correction that we have is we have to make sure that we're solving the right problem. It's not about systems engineering. It's about the engineering of systems. If you don't know where you're going, any road will get you there. We don't have to throw away the progress of the last 10 years, the last 20 years. But if we will recognize the true destination, digital engineering, the connected life cycle, transforming business requirements into fielded capabilities, well, then we can make a better stab at this next step of the journey. With that, I thank you, and we'll take questions.
Thank you, David. We do have a few questions, thanks to our participants. I encourage you to join the discussion now and submit your questions using the webinar control panel. If you do need to leave the webinar, please take a moment before you go to respond to the quick survey that will pop up on your screen. We have a few questions from a couple different Jacks. So the first Jack asked, I like the statement, the right information at the right level, knowledge-based. What do you need to add for decision makers with skin in the game to rely upon this information?
It's a great question, Jack, and it gets back to the concept of trust. Donna Rhodes at MIT is doing some great work in this area. And by the way, for those that don't understand it, Donna Rhodes is a great systems thinker, a great systems engineer, and her PhD is actually in anthropology. So it gives her a unique perspective on humans and society. And that's where it lies. It's a trust issue. And what Donna's research in conjunction with Adam Ross has shown is decision makers do not trust models. They trust people who trust models. And so we have to recognize the human role in this bit. Now, can we change that over time? Perhaps. And I think the key there is actually transparency and translation so that we're using the language that the decision maker is comfortable with. But in the interim, let's recognize that there's actually this, the trust follows a proxy step. The decision maker trusts the person who uses the model. The person who uses the model trusts the model.
Okay. So from the second Jack, if information is so central, then please tell us what information is and is not in your world.
So let's use the data, information, knowledge, wisdom type hierarchy. So if we take a step back and look at what pieces of data are, well, we know those from the systems engineering world. They're things like requirements, they're things like functions, they're things like components, but they're also things like risks and concern and verification and pieces that are not specification. But that's just pieces of data. If we want to begin to transform to information, what's critical are actually the interrelationships between that data. And that has to be treated as first class. Remember, emergence in a system comes from relationships. Systems engineers have to be obsessed about the relationships. So if we will look at requirements in context, how they interconnect to the behavioral thinking into the actual physical instantiation and that knowledge network, that is what I would classify as information at the system level. And to me, that becomes the connected architectural model. And I think there's one and only one architectural model. There's not a separable requirements model. There's not a separable physics model. Sorry, physical model. But instead, that information model can be viewed from multiple viewpoints for particular slices, for particular decisions, et cetera. But take those atomic pieces of data, put them in context with rich relationships, and that to me is the information that is essential in this context.
Okay. So the next question, also from Jack, is do you recommend TEVV or fit for purpose expectation?
Jack, you and I may need to follow up offline to get to the level deeper. Based on the way the question is asked and just my first instinctive reaction, it goes to fit for purpose, okay? And the reason I say that, but I would like some clarification offline, is fit for purpose inherently deals with context, and context is critical. Decisions outside of context, information outside of context, takes some things and makes them implicit. And anytime you're dealing with implicit information as opposed to explicit information, you have the opportunity for miscommunication, misunderstanding, misapplication. So in my first level understanding of what you're asking, I always tend to gravitate towards fit for purpose, but we may need to go a level deeper offline. If you will, send me an email and I'm happy to do so.
Okay, I'll make a note for you and Jack to get together. He did come back over your information. Can you give us anything about what is not information?
It has more to do with what information would not be relevant at the system level or for the architecture or analysis or actually decision. So part of this, when you're dealing with an information model for systems engineering, or more specifically for the engineering of systems, is recognizing when accuracy is sufficient and when you need to be precise. And so as engineers, we move through levels of abstraction, and we don't explicitly deal with detail that is not necessary for the piece at hand. So everything is information, everything is valid, but it's the engineering insight and judgment to really be able to say that that's not appropriate at this level of abstraction, that's not necessary for this kind of decision, et cetera. Scoping.
Okay. Our next question comes from E. Walker. It's how are you selling sub-optimization to the current AI ML crowd that is hyper-focused on full automation?
I guess the good news is I have not had to deal face-to-face with that crowd yet. So, you know, anything that I say here is hypothetically how I would deal with it. You know, it's going to come back to our same precepts of systems engineering. There are not many laws of systems engineering that we know, but one of the few is that optimization of the component will not optimize the system. And therefore, rather than getting pulled down into a technical discussion at the digital level, I would try to pull that conversation up to the system level and help shift the context. In doing so, I don't want to attack the value that they're bringing because they're bringing real value. I just want to help them apply that at the right level so that they become a partner in the journey as opposed to a naysayer and a critic.
Okay, we have one more question unless other questions pop up. So if you are thinking about giving us a question, please go ahead and use the control panel to ask. This is from Ricardo. How can we keep smart and be aware of the model's intrinsic limitations when we start building upon them? There is a balance on trust.
There is, and so Ricardo, this is hitting the aspect that, to be honest with you, I have not seen industry begin to address. And what happens is we begin to model within a context, and we may or may not state that context. The engineer tends to remain aware of that context, and they begin to flesh out. They move from an implicit thinking to explicit. So within a context, they will develop a very explicit and defensible representation of knowledge, and however they do it, whatever kind of model that is. But the modeling of the context, or more specifically, the representation of that context, is not explicit. And that is why the human role in trust is so critical right now. We need to, as engineers supported with semantic scientists, start to talk about not only how do we represent the thinking within that context, but how do we explicitly represent that context? Yes, you can make descriptive statements, you can state bounds of validity, you can state all those things, but we're doing so at a relatively low level of fidelity. If we want to get to a point where we can actually achieve model reuse, then we're going to have to figure out how to represent the context of a model with the same type of fidelity that we represent the model itself with. I don't have the answer for you, Ricardo, but I do have the challenge that we as an industry need to focus on context far more than we do.
Okay. We got a response from Jack that says, Wymore shows that unless optimization of components also optimizes the system, then you do not have a system. Do you have any thoughts on Wymore?
Well, Wymore is, is the true deep thinker, particularly when you bring the mathematical dimension here beyond just basic descriptive principles. And so there was a long-standing bet on, if you could read the full Wymore and fully digest it, that there was a steak dinner in it for you. That bet aside, which is a little tongue-in-cheek, Wymore is a reference that we need to remember and we need to leverage in this journey. In fact, it's a dimension of model-based systems engineering that most have forgotten. So Jack, thank you for that pointer to it. And we need to figure out how to leverage Wymore and inject Wymore into more conversations and more of the evolution of our engineering life cycle, or we will reinvent the wheel and probably reinvent the wheel wrong.
Okay, we have one more question, and this is from Alan. When you engineer a system, it is fairly straightforward to understand the context of that system. However, when you address the engineering of systems, doesn't your context grow your scope such that it becomes difficult to manage? How do you address that?
So when you talk about engineering a system, and you're speaking to the context, I believe that you're speaking to the environment or the system of that system, sorry, the context of that system itself. So you're talking about through life physical context. And yes, that is easy to draw the bounds of validity. The same thing can be true, honestly, when you talk about the engineering of systems, if you will talk about really the archetype of system that you're talking about. So here's what I mean by that. oftentimes we talk about systems engineering in the true general case. What are the fundamental true principles that would apply if I'm engineering a brand new spacecraft or a brand new insulin pump or a next generation insulin pump or a bicycle, okay? So we're trying to define systems engineering at the complete generalized level. When you do that, defining the context for the engineering system is very, very difficult. But if you will look at it within the scope of your engineering enterprise, which then is tailored based upon the types of problems that you solve and the subject matter expertise that's required to solve them, and other things about how you do engineering and honestly how you do business, that dramatically reduces the scope. And now you can actually be far more crisp in your statement. And I believe that you can define the context for your engineering system, the system that is doing the engineering of systems. Okay, so don't be universal. Look at your enterprise, look at the type of systems that you build. Are they precedented, unprecedented, what specialties, etc. If you do that, now you can have a real bound as opposed to hypothetical bounds, hypothetical context.
Thanks, David. That wraps up the final Q&A for today's presentation. I apologize if we didn't get to your question. We will contact you directly to ensure that it has been answered. If you have any other questions or comments for David, don't hesitate to send him an email. You can see his email address on your screen now, or you can post your question and comments on our LinkedIn group page. Just visit linkedin.com and search for Vitech Corporation. Thank you so much for attending today's webinar. Please check our website for our upcoming presentations. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Once again, thank you for joining us and have a wonderful day.